It's a pleasure to introduce Laurentiu Maxim and from the University of Wisconsin-Madison, and he will talk about linear optimization via Chern-Mather classes.
Okay, thank you. Well, thank you, Pepe, for inviting me. This is a great place. So I always thought that characteristic classes are a beautiful subject, but I also wanted to, I think we can sell it better if we give some applications. So I entered this this optimization business through my collaborators, all young and bright. So I'm just, reporting mostly on our joint work. Parts of this have been talked about in various other places. Some of you have seen it before. So there are also questions that I want to ask. Pepe, as you know, put together, maybe he's still doing this huge collection of handbook of singularities volumes. So this which volume you are now? In volume 7, which I think is published now, it's gonna be published this month. Volume 7 contains a long survey about these things. So for people who want to see just everything at once, that's maybe a good place to start. So this is mainly an application of Ginsburg's approach to Chern classes via microlocal calculus. And this was revived recently by Paolo, Leonardo, and York. And we took advantage of their work and sign fixing, and we used it. So I'll tell you how we used it. All right, so let's move on. I have a bunch of sections here from trivial to not so trivial, and we move hopefully at a slow pace, and when you tell me to stop, I'll just stop. So the first, this is obvious. I just wanted to set the notation. So we have the constructibility business, constructible functions. These are just constant along strata, integer functions, constant along strata. There is an unconventional notation for constructible functions. I use CF. We saw other things earlier, so this will be the group. We have the basic distinguished basis for constructible functions given by indicator functions of closed subvarieties, local Euler abstractions of closed subvarieties that you saw earlier. They were asked earlier. And then we have this Euler characteristic. And there are other bases, but I'm not going to make use of them. These are the ones I plan to use. And you can use any of these bases to define an Euler characteristic on this constructible function group as a linear map defined on generators by the usual Euler characteristic if you plug in the functions 1. So Jörg, I see you're already about to burst, so feel free to talk. We can plug it back in. All right, so Chern classes, again, this is very familiar to all of you. We have this natural transformation from constructible functions to Chow or homology, Boyle-Moore homology, with the usual normalization property. And I want to set the notation. So for locally closed subvariety, I'm going to call the CSM class the value of an indicator function of a subvariety, of that subvariety. It's valued in the ambient Chow of the ambient space. And then the same with the local Euler abstraction. So this will be the main ingredients. So for the function 1, this is usually referred to as the CSM class, and for the local Euler abstraction of the subvariety, we usually call it the Chern-Mather class. That's subvariety.
But the important point for you is you really only want to have
locally.
Classically, people only do this for close.
Right. So here you have to. But we really take advantage of the fact that when you work in the Grotany group of constructible complexes, the derived push forward and the lower Schrick are this. All right. Yeah, so I extend by 0. So this is how I regard these functions. I mean, you can work it out with stratifications, but you can also think just extend by 0 to the ambient space.
So if you work in the locally closed, then the Euler abstraction of the sum of the strata is not the same thing as the sum of the Euler abstractions.
All right. Good. So, yeah, so I want to introduce this conormal business, the characteristic cycle. This is done to characteristic cycles. So the conormal variety of a closed irreducible subvariety, let me start with this for now, is the usual thing. So take covectors which are vanishing on tangent spaces to regular points um, in the subvariety you work with, and then they form these are irreducible conic Lagrangian cycles in the cotangent space of the ambient smooth. So now I work with an ambient smooth variety. I want to have a cotangent bundle. Yes.
Do you close it?
Closure up, yeah?
Yeah.
You didn't mention, you close this up.
You take the Zariski close.
Take the close.
Ah, there.
Yeah.
I missed the closure. That is, now I'm fine.
Of course, we should close it. Everything is closed. And then we take the free abelian group spanned by this conormal varieties associated to irreducible, closed irreducible subvarieties in the ambient, and we have this characteristic cycle transformation, which gives you an isomorphism from constructible functions to this irreducible conic Lagrangian cycles. Well, to conic Lagrangian cycles, which on a basis, you can take this as a definition if you haven't seen it before for the characteristic cycles. I told you that these EUs are the basis of constructible functions, so we can think of this as being a definition. So up to assign, just assign the conormal variety of the subvarieties here I work with. All right, so I told you earlier that we all know that the Chern-Macpherson the Chern class transformation is defined on this group of constructible functions by this characteristic cycle functor. You should now have a definition of Chern classes on this group of Lagrangian cycles in the cotangent of the ambient. And this was worked out, maybe up to science, by Sabah, by Ginsburg, yeah. And then, as I said, very recently it came up in the work of Paolo and Leonardo and Europe. Chen-Zhang, yes. I always forget the fourth collaborator. I also have a fourth collaborator here. I always leave him out. You know,
Not do.
I think my attention span only goes to 3. All right. So I want to explain this quickly because this is a pretty story coming from intersection theory. It has many other applications. So we have this microlocal interpretation of Chern classes. Again, we have a smooth ambient variety. And let's say we start with the rank R vector bundle, call it E with projection pi. For us, later on, this will be the cotangent of X. And you take the projectivization, the projective completion of this bundle. So I'm projectivizing also the fiber. So the complement of E in E bar is just the projective bundle of E. Right? What do you call this? Projectivization of E. Yeah. So there are projective completion and projectivization. So these things are usually easy to mix up. So we need to get it here. All right, and then I take this class C to be the Chern class of the hyperplane bundle on E bar, on this completed bundle E bar. Okay, now we do intersection theory. So for a conic, irreducible conic subvariety in E, as I said, for us this would be the conormal varieties later on in the cotangent bundle of X. We get an induced R, also R, dimensional cycle in the Chow group of E bar, and intersection theory, you can look in Fulton, for example, tells us how to write this cycle in E bar in terms of things coming from the initial, from the base, right? So you pull back certain elements from the Chow of the base, you pull back to E bar, and take cat products of this with powers of this Chern class C. All right, and this is what is usually referred to as Chern classes of the conic subvariety C. So these things you pull back from the base. their sum is usually called the shadow by Paolo, and
But this notion Chern-Mather, I think you have chosen. I'm not sure if this is the standard.
I think Paolo uses this. Don't you use this? No?
So if this C would be a vector bound, then it fits with the definition of Chern class of a bound, and this is the story of Grothendieck. If you have first Chern classes, how to get the higher
Did we
Chern.
use that? Did we? I thought this is used by other.
Yes, yes, as operators. Yeah, you use a positive boundary structure. But for cones, I'm not sure if this term.
Well, you use Segre classes. Why wouldn't you use Chern classes? I don't know. It's the same.
It's a matter of terminology, but Fulton does not have a Chern
Yeah,
classes of codes.
Yeah, but they use the Segre classes.
You use a second class of cones.
They only differ by.
Chern class of cones.
All right.
For bundles, one is the inverse of the other, but for codes, you cannot take the inverse.
Yeah, but I mean they're still related in the same way, right? By the Chern class of the bundle E. Anyways, let's call it the Chern class. Chern class is of the conic of the cone C. So their sum is referred to usually as the shadow of C, right? I don't know who came up with that terminology. Maybe Paul. All right. So now a quick observation: if this conic subvariety is supported on just on part of the bundle coming from a closed subvariety in the ambient, then you can write these classes just as the push forward. So these classes are in the chow of the base, right? X. So they are only supported on Z. Push them forward and we get this. The point here is that they vanish above the dimension of the subvarieties. So it's on the nose. So if I have something with support on a subvariety, I don't have Chern classes in dimensions bigger than the subvariety. Okay, and then of course for calculations, it's important to treat the trivial case when you have the bundle E trivial, in which case this formula becomes actually quite easy. It's just essentially product to linear subspace. So this will be used, this is actually used in calculation. This is the only formula that's used in calculation for our purposes. All right, so what's the reason for terminology? As I said earlier, if you just work with the bundle being the cotangent bundle of the ambient smooth variety X, then this proposition, which is again Sabag, Ginsburg, and now I have 4 letters there, so there are all 4 of them, tells you that this Chern class, the usual Chern classes of a constructible function phi are up to a sign, these Chern classes that you get from this construction applied to the characteristic cycle of the function.
But here you should not attach our names. This is from the 2 others.
Yes, but you know, I'm a friendly guy, despite what others think of me. I think some the others have maybe some signs or they know some signs or something.
Ginsburg makes sign mistakes, so you have to be careful.
It's not necessarily a sign mistake. It may be absorbed into a definition. I mean, it's a matter of convention. You have to.
In other places in the paper, sign mistakes. So Ginsburg's paper, you have to be careful. But what he calls Chern classes are in our notion the signed or dual Chern classes.
Right. So these things on the right here are what we usually call the dual Chern classes.
Maybe the other comment is about the projective completion here. The completion is more natural because then you don't lose the zero section.
Exactly. You want to also take cones in the zero section. When you just projectivize the bundle, you lose this. All right. Now we have the typical story is that you work with the smooth, let's say the complement of a divisor in a space, and you want to understand, you have a constructible sheaf or constructible function on that, and you want to understand its Chern class. So it's natural to consider a compactification, but it's more natural to work with a normal crossing a simple normal crossing compactification, and you actually can construct, well, you can compute the the Chern class of a constructible function on the open piece from the compactification. So this is an idea that's used a lot in algebraic geometry, and we, let's say, I think Ginsburg has a formula for the characteristic cycle of a push forward under an open embedding, and this is what we use to reformulate the calculation of Chern classes for open submarines. So let's, and this was, I mean, by now it's already generalized in several other settings by Paulo's former students. But for our calculations, we only need a nice compactification by a normal crossing device. All right, so that's the setup. I have an ambient smooth variety. I have a simple normal crossing divisor in that, and take U to be the open complement of the divisor with inclusion J. And now you have logarithmic forms on X with poles along with the, you have one forms on X with logarithmic poles along D, and take the vector bundle associated to that. Let's call it T star XD. So this is an extension of the cotangent space of the subvariety U, and in fact it contains this cotangent space of U as an open subset. We're going to work with various closures of Lagrangian cycles in the cotangent of U, and this is one space where we close up our cycles. In fact, yeah, so if I start with the conic cycle in the cotangent of U, I take its closure in this logarithmic cotangent bundle, and let's denote it by, so C bar is the closure, and log comes from the logarithmic condition. Okay, and then we have this result which is formulated. You can ignore it for now. It's just, it relates the classes I was trying to understand. So take the characteristic cycle of a constructible function on U. Regard this function just like we do with local error abstractions and so on. Just regard them as functions on X. And then in the cotangent of X, calculate this microlocal Chern class like I defined it on the previous slide. And this can be calculated by the left-hand side, where I'm taking now the log completion of the characteristic cycle of phi in this cotangent log bundle, and I do the Chern class calculation, microlocal Chern class calculation is in the previous slide. So these are two different bundles. The left-hand side has the benefit of this simple normal crossing compactification. And we'll see why this is useful.
Yeah, the benefit of the left-hand side is also you just take closures. On the right-hand side, it's very complicated.
Right. So this is
the characteristic cycle.
So maybe since I have a marker, so if I have a constructible complex on U, and I had this inclusion J, of course I can take the push forward of this complex, and I take its characteristic cycle. Well, now this is a characteristic cycle. This is the conic Lagrangian cycle in the cotangent of X, and I want to take its Chern class. This characteristic cycle was calculated by Ginsburg, right? So, but that formula is not very useful for this calculation of the Chern class, so then we use the other completion. So you can also complete the characteristic cycle of F directly by this logarithmic business and take its Chern class in the log compactification. So these things are not, the fact that they are related should not be surprising. This is how we calculate variance in algebraic geometry, right? In birational geometry, to this log compactification. So this is the same philosophy. All right, so there is a formula here which eventually I'm going to make use of, and of course I would like, for practical purposes, to have the cotangent is usually complicated, right? But I want to complete here by something which would give me maybe a trivial bundle, like think in toric geometry, right? And then this formula becomes very simple, as you saw on the one of the previous slides. So this is the benefit of this sort of calculation. So I have some freedom once I compactify to a trivial or something close to a trivial log bundle, I have a chance of actually computing. So we're talking about computability. So this is one reason why I'm doing it. Okay, so yeah, I put the formula up there again. So let me just say that at the degree level, this formula was, and in fact, was motivated. Our formula was motivated by the respective degree formula proved by Lei Wu and his collaborators do. And then, of course, for the function one, so this is the first constructible function you can think of on this open subvariety U. This is the classical formula of Paolo. I know everyone should perhaps know. Okay. And of course, I mean, again, if you work with nice compactifications, the point is that this log bundle or some twist of it would be trivial. So here you don't get much contribution. All right, so now let's move to this linear optimization and Chern-Mather classes of affine variety.
So what are the cases in which you get a trivial bundle?
Take a subvariety in a complex torus. Yeah, so then the compactification is by coordinate hyperplanes.
Any subvariety, it doesn't matter if it's one circle.
That's exactly the point. It doesn't matter. Because in the end, you see, I'm still working with constructible functions on this. They are defined on Z, which is closed in your U in the torus, and I can always regard them as here.
I can take anything in the projective space, right?
Yeah, but this is, people have looked at that already, so I'm not, Paolo has done lots of calculations in that situation. So this is the toric situation. These are nice. They have nice compactification. But in the affine case, so if I just take now, so I said the good situation is when you take C star to the n, let's say in Pn with the coordinate hyperplanes, right? I don't know, HR or something like this. So this is a simple normal crossing compactification. But if I take just C to the n inside Pn and then hyperplane at infinity, this is not. This is not sorry, it is a simple normal crossing compactification, of course, for stupid reasons, but the cotangent bundle is trivial here, but it's not here.
So you want very affine, something like very affine.
This will work too, and this is the setup of this situation. You just have to twist a little. You need to be a bit patient. Yes, that's all. I'm not saying it's an easy calculation, but it's a kind of routine calculation. All right, so let me relate to linear optimization, because this is something that some people like in linear programming. For example, they want to understand when a linear function has, it's optimal in some sense. So the linear optimization degree. So this story with optimization is you have usually maybe I should have put this here. You have an objective function which you want to either maximize or minimize on some model, which is usually an algebraic variety. For us, it's an algebraic variety. So the way you do this, you first look at critical points of that function. Of course, you can do this in a stratified setting where you can restrict to the regular part of the model of the subvariety you're looking with. Right? And first, people don't calculate by brute force, or some do calculate these critical points by brute force, and then they see which one does the job. Or if you want to cheat a little bit, you say, well, how complicated is the problem? And then you try to see, to analyze the complexity of the problem by counting the number of critical points. If you get very few, then the problem is perhaps solvable by a computer quite quickly. If you get lots of critical points, then perhaps you should do something else, right? Go have a coffee, let the computer work. But anyway, so this, yeah.
So if it was not an affine variety, but a projective variety, then this would be the degree of its projective duo. Right?
They are always, yes, so they're always real. That's why they're called degrees. They're always degrees.
Degrees of the duo.
Yeah. Yeah, you can think of it like that. Yeah, yeah. So again, I think the projective situation was already addressed by Paul. So everything in the projective case was already addressed by Paul or follows from Sabah. So here I'm trying to do the affine situation with no assumptions on infinity. So this is actually the only change. So it's a very general situation. So I'm taking a affine subvariety, and I take a linear function on the ambient space, restricted to zero to the regular locus of the subvariety, and count the number of critical points. So maybe I should say it's a general linear function. So I want a complex Morse function, right? So I don't want bad singularity. All right, and this can be realized by microlocal geometry. It's called degree for a reason. It's really the degree of a projection map from the conormal variety to fiber direction. All right. And this was, of course, it appeared already in the work of Pepe and his collaborators, and they didn't call it like this because they didn't have any reason. But counting the number of Morse points of a more complex Morse function, this is a problem that solves the singularity theory.
But the reason of it, here you work with singular spaces and you only look to the regular part. That is the reason in the end why the Euler function.
Yes, true. And this is their observation, I think, or stratified Morse theory tells you that.
But that's the rule of the Euler function.
Yeah. Okay, so that will come in. So we can do more. We can define what's called bidegrees. So these are this is a slight change in setup compared to work of Sabah or Paolo and people who work either on the chow of the base or push everything in the ambient projective space by closing them. So here we're taking still an affine subvariety, and what do I do with this conormal? Let's write that down here. So I take this conormal in the cotangent of Cn, material bundle, and I complete it. I close it in Pn cross Pn. So I take this closure in Pn cross Pn. So what people usually do, they just take the projectivization of this thing. So they just close the fiber direction and occasionally work over the base Z and then push into the ambient. So this is a slightly different flavor. I work with locally closed subvarieties in Pn, and I may have bad behavior at infinity. So anyway, so you take this closure and then you regard this closure in the chow of Pn cross Pn, just write it in the basis of the chow group, and you have some numbers here, integers, which are called bidegrees. Now these bidegrees, of course, they are all degrees, right? So I just intersect this linear subspace, this product of linear subspaces with the complementary ones, generic complementary ones, and I get, or I intersect this conormal variety with the product of complementary linear subspaces for each of these products, and that will give me this BR. So these are really degrees of intersections of cycles. Okay?
Intuitively the same information as the coefficients of the Mather class.
Oh, yeah, very good. You're seeing through. All right.
That you only sum up to the dimension, that was your comment.
That was the comment because these are supported on a d-dimensional field, right? So d is the dimension. There are no further species. Okay. So at the degree 0 level, I mean, this B0 is just the initial degree I mentioned earlier, but of course the other ones are still, well, they should be read off by something, and that's where Chern-Mather class is coming. All right, so this is the title there. LO bidegrees determine the Chern-Mather class. So we do the usual thing. So fix the standard compactification, look at the local error obstruction function of the affine subvariety Z, that's a constructible function on Pn, extended by 0. And then we have the Chern-Mather class, but now of Z, but now I regard it on the chow of Pn. So I regard this local error obstruction of Z as a constructible function on Pn, and I just take its image under the Chern-Mather transformation, then we get the Chern-Mather class of Z. And this has some coefficients. This is the standard, the usual thing, right? So there's some components in each degree in the chow of Pn. And now the natural question is, how are these AIs related to BIs? And the title says they determine each other. And the formula looks a bit complicated, but it's really just, maybe I'll say on the next slide how you derive this. It's really just the calculation. So it's by brute force. I am in this setup. I have to consider this compactification of Cn. And the log cotangent is not trivial, but I'll say it on the next slide. The twist of it is, so then you have to use Segre classes, etc. All right, so this is the conclusion. Maybe I'll hide this formula from you for now, but I'll say some consequences of it in a bit. So yeah, we work with the logarithmic cotangent bundle for the usual compactification of the affine space. This is not a trivial bundle, but upon twisting by this hyperplane bundle, you get something trivial. And then you're calculating, you're saying, okay, I'm not taking the closure of cycles in T star U being Cn now. I'm not taking the closure in E, so that the local tangent in this case would be E. But I'm taking this closure also in this twist of E. And then I want to see how Chern classes of these two guys differ. So I want to calculate it here to apply our formula, but this is more convenient because it gives you a trivial bundle. And then these guys are related by the usual calculation of Segre classes first and then Chern classes. Yeah, so I wrote it here that it just tracked the relationship between the Chern classes of the closure of this guy in the two bundles.
So you mean they have the same projectivation, but you change the role of what is the tautological boundary?
Exactly. Yes, exactly. All right. So this is a calculation that's inspired from a paper of Paolo from the projective case. It's very similar in speed. All right. Now applications. If you, well, you guys should tell me when I have to finish. I don't think I'm close yet, but just do this.
25 minutes or more.
All right.
So we have chairwoman taking care of it.
Identifying, so I had this formula relating the AIs and BIs, and I told you that B0 was this L of degree, the number of critical points of a general linear function of the regular part of the subvariety. So now identifying the top degrees in this formula of AIs and BIs of the Chern-Mather components and this bidegrees gives me exactly the formula for this L of degree. So this is exactly what Jörg was saying. This is where the local order obstruction comes in. So you have to take the local order obstruction of the subvariety, take out the general hyperfield. And this is a formula that appeared in a paper by Pepe, Mihai Tibar, and Gajowski a while back. So exactly this one. Okay. Now, if you plug in -1 in that formula, what you get is Late-Bézier calculation, and it appeared also in Paolo's work, and others also worked it out. So this is for a cone. So you're calculating so there was a question here, how do you calculate the local order obstruction? By what methods you're calculating it. This is just a special situation of a cone point. Take a cone on a projective variety, and then the local order obstruction of that cone point is the alternated sum of degrees. So this local, how do I call it? LO by degrees. Yeah. Of course, you can now reformulate this in terms of Chern-Mather classes if you like. But so this would perhaps not be too difficult. But anyways, we didn't do it here. So this is just This is the cone is a C star invariance. You have a C star action, and then you know, the local error obstruction is C star invariant. This is what you do. So what you're really calculating here is the Euler characteristic of the local error obstruction, but it's just concentrated at the point. All right, so these are quick applications of this formula. Again, no results. And then this slicing idea comes in, right? So I can do the same sort of or I can think of the same sort of invariance now defined not just for the initial variety, but for its general slicing by various linear subspaces. And I calculate the number of critical points. These are called sectional LO linear optimization degrees, sectional from sectioning. And now the question was, well, what are these things? Of course, we know how to calculate them from this paper of Pepe and Ibar and so on. So these are just Euler characteristics of the local error obstruction of slice. It's restricted to farther to the complement of yet another generic hyperplane. But then how are they really related to Chern-Mather classes or optimization, right? So this is the question. In degree 0, well, nothing happened because I don't slice at all. It's the usual L of degree. But then if you slice by a complementary dimension linear subspace, generically you get the degree of the subvariety. And then the question is, what are the others? And again, this is by brute force calculation. This is actually quite simple. Again, using some work of Paolo, you realize that these bidegrees of things coming from the conormal space give you the same information, or if you like Chern-Mather space, give you the same information as this section. Now, here, this is a bit different from this story with involution, but you get this formula for the bidegrees, right? So the bidegrees, things coming from Chern-Mather classes in a convoluted way, are calculated by this Euler characteristics of local error obstruction of slicing. So I think this is yet another way of, I mean, on the left-hand side you have Chern-Mather information, on the right-hand side you have Euler characteristic information, but it's not as explicit as the involution formula that Paolo has, and I guess Toro also did this calculation. So maybe Paolo, I don't know, maybe you have a comment.
You can also do without any, can do directly.
Well, it's done directly. There is no involution.
Yeah. So in principle, you can do it by Morse.
But I'm just saying, I mean, you can think of it now as being relating Chern-Mather to slicing. So this is yet another way of exchanging Euler characteristic information to Chern-Mather information. All right. Now, so we had a very stubborn referee for this paper when we submitted it the first time, who kept saying this was done by Sabah, or this was done by Alufi, or something like that. I don't know. I mean, this sort of, and we wanted to point out that this, I mean, there is this relation to polar degrees in the air, right? So in projective geometry, you have these polar varieties, you have these polar degrees. I'll say what these things are. And the assertion was that these things are always, these bidegrees or sectional degrees, what they were looking at, they're always polar degrees. And well, initially we didn't have this in the paper, but then we made the point that these are not. This is not, I mean, sometimes they are, but not always. So what polar degrees I'm referring to, take the projective closure in the projective space for your variety, and then you have, in this case, the projective conormal variety. So I can reformulate this now in terms of the closure in Pn cross Pn dual. So this these covectors, I can see them as tangent hyperplanes to regular points. And then, of course, let me put the two cycles we have on the same slide. So I had this closure of the conormal of the subvariety Z in Cn. I had this closure in Pn cross Pn. Write the formula for the bidegrees in the chow of Pn cross Pn. And then you can do the same thing with this projective conormal, but for the projective closure of our variety C. And you write it by degrees. These are called polar degrees. Of course, now the difference is that one of the cycles is n-dimensional, this is n-dimensional, this is n-1 dimensional, so there is some difference there, n being the ambient dimension. But in principle, it's kind of natural to think that these guys, these pairs of invariants, or tuples of invariants are the same. And we try to make that precise. And in fact, I think that the story was that one of my collaborators is very good at computers, and he kept plugging these things in, and occasionally, sometimes they would come the same, other times they would come wrong. And the story was what's going on. And this is explaining the next result, which says that, well, this formula was done in the smooth case already observed by Strofeld and his collaborators. So these bidegrees indeed are the polar, so bidegrees for the affine variety, they are the polar degrees for the projective closure, provided that the cycloplane at infinity is not in the dual variety of this projective closure. And this is an if and only if condition. So it's always true if you work with cones or things like this, but we have very specific examples when this identification fails. So of course, maybe I should say, so in optimization, people usually like to work with smooth varieties. Restricting to the regular locus is kind of a nuisance. You understand what happens in the smooth case, but also in the smooth case, you have cohomological classes, so you can do all this calculus directly. You don't have to, come to the singularity theory invariants like we do. And they get a lot of intuition from the smooth case. The thing is that if you work, I don't know. Anyways, I shouldn't say more. So there are some formulas in the smooth case that suggested that such a relationship should be also true for the singular context. And there is a glitch here that one has to take into account.
So in high school level, a circle is an ellipse is okay, a hyperbola is okay, but a parabola is not, because that has a tangent which is a hyperplane.
So, but it's smooth, but singularities are
No. So this is the whole point. So we want not to have singularities at infinity. Right. So if you have singularities at infinity, this thing usually fails, right? This is exactly what this is.
Yes, this is the reason.
Yes, exactly. It may seem smooth, but then it has singularities at infinity, and that causes trouble. Singularity theory still comes in, but it's in disguise. And of course, if you work in the smooth context, you may be tempted not to consider what happens at infinity. That's why people usually work projectively, right? Because you don't want to. Thereby, on the nose, if you take a generic hyperplane, everything is transversal, and that's okay.
So that's the difference here with local error such that you're using the usual ones, right?
Exactly.
If you don't want to have similarities and infinities, if that's the case, then you agree. Otherwise, it's a problem.
If you don't have singularities at infinity, everything is the same on the nose. But if you have singularities at infinity and we allow that case, then things may be a bit different. Exactly. Yes. And I think this was the main point, right? So we don't make any assumption on the singularities at infinity, which are implicit when you work projectively, and this requires some extra care. That's all. It's not too complicated, but it requires some extra care. All right. So now one application of this story with linear optimization. This is something that perhaps you saw already in some of my talks, but I want to give it as an application here. So you try to minimize the distance from a point in the ambient space to a given variety. That point should be chosen generically. Hopefully, if not, you have to do something else, a mortification or something like this. So of course, now when you want to minimize the distance, this is called the nearest point problem. You have to use the Euclidean distance function if you work in the real case, or its complexification if you want to do complex geometry. And of course, people when they do optimization, of course real geometry is simple in in principle, but it's very complicated for calculations. And then you complexify, and they have a lot of tools. Like we know, complex geometry provides us lots of tools for calculations. But you usually get many more critical points than you get if you just work in the real setup. So these degrees of optimization that come up here, these are all coming from the complex world. These are upper bounds on the complexity of optimizing the initial problem you're looking at. So just like in the linear case, I work in the complex geometry, so I take what's called the square distance function, but of course this is not a distance function in the sense we know, right? In the complex world, it's not that, this Hermitian distance. It's just the complexification of the usual distance function from the real world. And you're looking at the number of critical points of this function, the regular part of some model that comes up. This was introduced about 10 years ago to measure the algebraic complexity of the nearest point problem, as I was saying, for models in the real space with respect to a generic point from which you take the distance. All right, so then I have some result here that I wanted to show, to discuss quickly. We essentially calculated this Euclidean distance degree of any affine variety in terms of order characteristics of just the topological order characteristic if you work with a smooth model, or using the local order abstraction if you work with arbitrary varieties. And here, instead of taking out the hyperplane, you're taking out generic level set for the distance function, for the square distance function. So now, what's the relation in the previous situation? Well, it's just a linearization. This is what I wanted to write. But maybe I should say that this formula was motivated, well, from two directions. One, I think one was inspired by work of Paolo again in the projective case maybe. And the other one was there was an open conjecture about the Euclidean distance degree of a very specific model coming from computer vision. So there was a conjecture that these people left that was checked on computers up to, I don't know. So this is about reconstructing the 3D position of a point by just looking at 2D images. This is the usual. I give you pictures of something and you tell me what does something looks like in 3D. So this is the reconstruction problem. And, there is an algebraic model, and people are trying to estimate how difficult it is to do this reconstruction for that model. They left this conjecture, and this is done through this formula, which is, I mean, I'm not saying these calculations are simple, because calculating order characteristics of variety is by no means an easy task, but still doable. All right, so the proof is by linearization. You just take usual, maybe graph embedding or whatever embedding, so that this level set, any level set of your square distance function is obtained as pulling back a general linear function on the higher dimensional space. And then you apply this formula about the number of critical points of a generic linear function. This is to the image variety. This formula of Pepe and his collaborators. So I put this here because the proof is very simple, and of course we did this before this linear optimization discussion. But in a way, this kind of tells you linear optimization is the key situation one should consider. All right, and now I want to do the very affine variety. So this is somehow the easy case. So here there is something called maximum likelihood estimation, because you work with subvarieties of in an affine torus, and here things are a bit different. These are the models that people in optimization theory use are called statistical models. These are models of various probability distributions. And in this case, they define this maximum likelihood degree. This is, again, some notion that appeared even before the Euclidean distance degree, about 20 years ago. And This amounts to calculating the number of critical points of yet another sort of function defined on this kind of, on the regular part of some varieties in affine tori. And of course, these are multivalued functions, so you have to be careful what you mean by critical points. So you're taking, I look at these things as the generating points of the d log function. But such functions are usually called master functions. In maybe in hyperplane arrangement theory, I know Marchenko was calling them master functions. I don't know what the reason for that is. But in statistics, they call them livelihood functions. And the story is that you have some data and you want to measure the livelihood of data to, well, of what you see to feed the data. There is a livelihood function that one wants to optimize. But in this case, you want to maximize the livelihood. So this is why is it called the maximum livelihood degree. All right, so I said here these things come from algebraic statistics. These are selling words. Of course, people working in algebraic statistics don't care about Chern classes yet, but if we push hard enough, maybe one day they will come to us and say, hey. All right, so then there was an interpretation given by Jun Ha, again, maybe 15 years ago. He was still a student when he did this, I think. For us, in the smooth case, this maximum livelihood degree can be computed topologically as a normal characteristic. Just plain normal characteristic up to a sign, so no taking out various things. You're already taking out pieces from the affine space when you work with the affine torus. This was a beautiful paper which I think opened up various directions of research. And then it was extended to a singular case by Jose Rodriguez and Botong Wang using the local error obstruction function. So replacing the Euler characteristic by the local error obstruction function. And this is what I was saying the other day, that they reverted this procedure by, I'll say something about slicing sectional ML degrees, but they use the sectional ML degrees to calculate the local error obstruction as an alternating sum of ML degrees of slicing. And this is something that I assume is very similar. I know it's very similar to what Leif Dizier did, right, and other people. But I'm not sure how much they were aware at that time of references. So it was kind of fun to see them rediscovering this calculation.
Oh, it's not the latest C formula.
It's very similar in some sense.
Similar, but it's not the latest C formula.
Yeah, the latest year formula was the one that I had for the cone stuff. All right. So ML bidegree. So just we play the same game. I take now the closure again in Pn cross Pn of what's called the this is called the critical variety or something like this. So you're taking pairs of points and data points, so that one is a critical point of the corresponding master function for that data point. So take the closure, take the Chow class, and so on. Write it in terms of a basis. You get some binding. Okay. The same story. The first one is the ML degree as I defined it. The top one is the degree of the variety. And the question was, what are the others? And this is not as, in principle, not as easy, but this is more in the direction that Richard was pointing to. So these bidegrees are exactly Chern-Mather information. Don't need too much twisting around. And this is due to the fact that the log bundle for this normal compactification is a toric situation that the log bundle is 3. So the Chern-Mather class of a very affine variety, these are called very affine varieties, is computed exactly in terms of this bidegrees. This is an easy calculation using the formula I gave you earlier for the Chern-Mather classes in terms of conormal geometry and the fact that the log bundle is 3. Okay. So now, forgot. Yeah, so I already said this. I already forgot what else I wanted to say here. Yeah, so I wanted to say that one could do the same, one can play the same game, and in fact, this is not just the game, right? So people are trying to calculate this. Their motivation didn't come from calculating the bidegrees or Chern-Mather classes. Their motivation was from calculating the sectional ML degrees. So you want to start slicing now your variety just like we did before and take the ML degree of those slices. And there was a conjecture that Junha and Bernsteinfeld made called the involution conjecture, which relates this bidegrees or the Chern-Mather class to this sectional ML degrees. And if in the affine situation we had an equality on the nodes, so to speak, by root calculation, here things are not as simple. And there we had to use this involution, exchanging Chern-Mather and other characteristic information that Paolo and Toru, apparently 10 years before, worked out. And we proved this conjecture, and this is exactly where this formula comes in. So, I'll stop. Thank you.